Okay, so today we will start by defining what we call monoidal tetrahedron. So yesterday we finished by a remark about the third Frobenius indicator. So the theorem we proved. So remember that this remark is about when you have three objects which are isomorphic, and you represent a morphism like that. You make a label and you want to move the label, which is exactly what we are doing here. Then you have to put a multiplicative constant, and that will be used later. So now, monoidal tetrahedron. Okay. Let me write something in green. To define a monoidal tetrahedron, we need a convenient model for the tetrahedron graph. So the tetrahedron graph is as follows. But we want a model which follow our graphical calculus following our graphical calculus in a monoidal category. And we choose to represent every vertex as a morphism of the following form. Morphism like that. So you may have some name here. So you see here you have one vertex and three edges. So this represents a morphism. This is a morphism, a morphism, morphism. So you can say, okay, you can put one here for this one. And for this one, you can say something like that. And for this one, you can say something like that, etc. The problem of doing, you can do that if you want. The problem is that when you want to prove result about this structure, you need something more unified. Otherwise, you will have to go from one to another model for the morphism. So we choose to put everything like that. But to put everything like that, then we need to modelize that. That will require some torsion. So for example, so we choose to represent every vertex as a morphism of the following form, of the following unified form. Unified form, because it's more convenient. And then, the picture need some torsion. So let me see. Let me explain. Let me show you first. So all this part, in fact, is not in the paper. So it is just to explain the motive, to motivate, in fact, how we modelize the tetrahedron in a monoidal category. So let me show you at the graph level. So you start from that. Then you go like that. So you should convince yourself that these two graphs are the same, are isomorphic as graph. And then we need to do something like that. Because in fact, we want the edges to be in below. So, and we want something. Every edges should be in below. So you should have something like that. And then, so this is related to this one. This is related to this one. And this is doing that. That's okay. And then we make the torsion of that. So we need to move like that in such a way that all this edge will be below. So this is exactly like that. Okay. So this three way to represent, these are three isomorphic graphs. They are all the same graph here. But this is how we will represent the tetrahedron in a monoidal category. So then we will need an extra step. We will put some for the morphism, and then we will need to deal with proper zigzag relation in such a way we can do something which makes sense in monoidal category. So let me now so preliminary remark. Okay, so now let me define monoidal tetrahedron properly. Monoidal tetrahedron. Okay. Okay. So we will need to so how many morphism, how many objects we need? We need 1, 2, 3, 4, 5, 6 objects. We need 1, 2, 3, 4 morphism. So let me introduce this. So let's see. Be a monoidal category. With left dual. Let xi I equal 1 up to 6 the object in the category. And let consider the following morphism. So, of course, such a morphism is represented as a morphism from 1 to x tensor y tensor z. Okay, so this is type of morphism we need to introduce here. So consider the following morphism alpha in the home space, in fact the home set here, between the trivial object x1 tensor x2 tensor x3 beta in home set of morphism between 1, the unit, and x4 star tensor x3 star tensor x5 star. Then alpha, beta, gamma, delta. We need just for one. So alpha, beta, gamma in offset between morphism between the unit and x5 tensor x2 star tensor x6 star. Finally, delta in the home set morphism between 1 and x6 tensor x1 star tensor x4. So don't worry, a picture will come very soon. Everything will be clear. So let us define the labeled monoidal tetrahedron. So as I said, we will follow this model. Okay, so I will write the notation, the name here, but I will draw the picture in the next page. So we need alpha, beta, gamma, delta. So beta. So whoa. Beta. Yeah. Gamma. And alpha. And so as here, we need, so we have the three objects. So here you have x1, x2, x3, x4 is here, x5 is here, and x6 is here. And then you connect. So you put this evaluation map here, an evaluation map here. Next, here you have an identity here, evaluation map up to here, Then you have an evaluation map identity, co-evaluation map, evaluation map. So it's a zigzag. In fact, this zigzag is only required because for the picture. Otherwise, you can directly say, okay, we go from here to here. But because of the pictorial representation, we need to put a zigzag. But this is the same as identity, so it's no problem. So, did I already make a mistake? Yeah. This is not here. This one. So, co-evaluation map, identity, evaluation map, identity. Okay. Then this one. Evaluation map, identity, co-evaluation map, some zigzag here. And finally, big evaluation map. Okay. So you should you should observe that alpha, beta, gamma, delta are exactly in these home spaces. So for example, alpha, x1, x2, x3. So that's okay. Between 1 and x1, tensor x2, tensor x3. Beta, between 1 and x4 star, x3 star, x5 star. So 1, x4 star. So it's evaluation map. You have a x4 star here. Here x3 star, and here x5 star. So 4, 3, 5. Okay, that's okay, etc. And you see everything. So here is a zigzag. Maybe it's not very well written, but this is well defined in a monoidal category. You have 4 morphisms, and you have some evaluation and co-evaluation map and identities connecting all these morphisms. So if you want, I will not do because it will be a mess, and it's not the point of this. This kind of representation is really adapted for graphical calculus. But if you don't like graphical calculus, you can, as an exercise, try to write the formula for this picture. If you like. It will be quite complicated to write a formula, but it's possible. But we don't need, because the graphical calculus is well defined. So here, it's okay. So this is our monoidal tetrahedron labeled with morphism. Okay. So what about this? What can we prove about that? So the observation is that here, if you write a regular tetrahedron like that, or even in a 3D, you have symmetries. For example, here in 2D, you have these symmetries. You have the cyclic group of order 3 as a symmetry. And yet, when you look at it as a regular tetrahedron in 3 dimensions, you can have some extra rotation, etc. Which, so the group of symmetries is something like the alternating group of 4. His orientation preserving, if I'm not mistaken. I wrote that in the beginning. Yeah. orientation preserving of the 3D tetrahedron regular tetrahedron is the symmetry group. Symmetry group is alternating group A4. So what we want to prove here is that this model is invariant by this A4 symmetry in some sense. So we can deform, and that's why it was important to have something uniform, because we will deform the drawing in such a way we get something equal, but where the morphisms are permuted, and with potentially some extra pivotal structure or some extra, you apply the map row, and we define this. So we will prove two such symmetry, and these two symmetry will correspond to a cyclic permutation. We generate the alternating group A4. And so up to adding the appropriate, up to applying this natural transformation we defined yesterday, rho and sigma, we recover this A4 symmetry at the monoidal level, which is very, very convenient. And in fact, we will see that when we will reformulate everything at the fusion ring level, at the spherical fusion ring level, then we will be able to provide a model for the tetrahedron, which will be much more closer than that. Anyway, but for now, we need to deal with this big jellyfish. So, okay. So, proposition. Proposition. Five. So following the previous definition, monoidal tetrahedron, we have the following cyclic symmetry, cyclic permutation symmetry. So alpha, beta, gamma, delta is equal to T of rho alpha, delta double star, beta, gamma. So here we get this cyclic symmetry for these three last morphism. So this come here, this come here, and this come here, up to some pivotal structure, etc. And you can iterate, in fact, this equals this, but you can apply the formula now here again and again. So this is equal to that bit. So sorry. So it's the other way. So gamma double star, delta double star, beta, and again is equal to T beta double star, gamma double star, delta double star, delta double dual. And so this is equal to alpha double. So this one is, so the applying 3 times this natural transformation, 1 time, 2 times, 3 times. So it's exactly taking the double dual of the morphism. So you get that. So you get finally that this, so you have this symmetry, and you can apply it again. And what we get here is that, in some sense, this is equal to this. So if you put double dual everywhere, it's invariant. Okay. So what time is it? So proof. Proof. So as I said, we only need to prove the first equality. The other is just iterate the first equality. As the other one come by iterating and applying 3 times this natural transformation is the same thing as the double dual by definition. By definition, is exactly one time, which is exactly the double dual. Okay. So we will need to apply some previous lemma in the preliminary section 2. And this previous lemma is saying what? So we will apply the previous lemma to some previous lemma to, we will consider 2 parts, this part and this part. So this is a morphism. So you consider this part as a morphism and this part. So this part as a morphism can be seen as a big you can see as some big morphism with three things. What are these 3 things? This one is first here, one is here, and one is here. So you have these 3 things can be seen like that. Okay. So, and the previous lemma, you remember this lemma 2.4 was a lemma. So you have this lemma was something that you have something like that, and you swift you have alpha and beta, and you swift you have beta double star alpha. I don't remember. You have something like that. So we will apply this lemma to this component and this component. Okay. So we will put this one the other way by putting a double dual, exactly as we proved in the preliminary section. Okay. So apply lemma 2.4 to this monoidal tetrahedron with x equal x6 tensor x1 star tensor x4 and y equal 1. So x6, x1 star, x4. This is exactly what we have here. x6, x1 star, x4. So you immediately get that T of alpha, beta, gamma, delta is so exactly the same picture as before, but with the delta on the left and the double dual. So you have delta double dual, beta, gamma, alpha, beta, gamma, delta. Yeah. And you have the alpha here. And so you have to be careful. In fact, you have to be careful to how. So you have this big part. So this is okay. This is the same as before. So alpha. So the left, this one on the left is connected to delta. So now delta is on the other way. So you have, so it was connected to delta like that. But now delta move here. So you get something like that. So okay. So the second edge of alpha was connected to gamma in the middle. Everything is a zigzag relation. So that's everything is made of evaluation and co-evaluation map. And the third here, like that, and beta, like that. And finally, you have that. Okay. So you have to convince yourself that when you apply lemma 2.4, so this component and this component, so you have one branch here, one edge. So this is the right edge of the B component, and this one is the middle edge, and this one is the left edge. So then you put delta here, delta double star here. So you have to connect like that. So when you draw the picture and you rearrange everything up to, you get that. Okay. And this has the form of the initial monoidal tetrahedron up to applying some natural transformation. For example, alpha here, so you have 1, 2, 3 going like that. Initially, you have only what is it? So initially, this one was connected to the one on the right. But now, this one is not connected to the one on the right. This is not correct. This one is connected to here. So this one is connected here. So we want to make this one first, how to do that? In fact, we apply the natural transformation row. Then this becomes the first, second, third. And then you really have the form we want. So it is equal to row of alpha. Here you have double star, delta double star, beta gamma. So which is what we wanted to prove. So in fact, yeah, up to drawing everything cleanly, there is nothing complicated here. You just have to draw it and to apply this lemma properly. And you exactly get that. And to recover the shape, the initial shape, you need to apply this not here, this natural transformation such a way that now the new box, which is this one, has the left leg connected to the one on the right, exactly as we want to do in the model. Okay. So, okay. So another remark also here, I wanted to, it was convenient to minimize, to simplify as much as possible the use of dual and left dual. Here we only assume the existence of left dual. We did not assume the right dual. Such a way, if you assume the left or the right dual, maybe you can move on the other way, or how to say, maybe you can modelize, you can find another model doing something like that, I don't know. No, it's not clear. Anyway, the advantage of this model is that we don't need the right dual. It works for the left dual only, existence of left dual, because you only have the evaluation map from x to x star, x2 to x2 star, x3 to x3 star, etc. You can manage everything with left dual. Okay. So as I said, more you will add structure to so monoidal category with left dual, fusion category, spherical fusion category, etc. More you add structure, and more you will be able to have a model which will be close to the usual regular tetrahedron. Okay. But for a general monoidal category, only left dual. I guess that this is the simplest way to get tetrahedron. Anyway, so we proved the first symmetry. And as I said, the rest follow by iterating. And the last equality is just that. So we are done. So remark. In fact, what is really amazing here is that you can prove, assuming existence of pivotal structure, you can prove this equality directly. So this is quite interesting because we were able to prove this equality without assuming pivotal structure. And in fact, the existence of a pivotal structure is an open problem. So, I don't know, maybe such equality can be used to solve this open problem. I don't know, it's just a remark like that. You can prove that directly using the pivotal structure. The existence of a pivotal structure is an open problem in general. So maybe this equality can be used, I don't know how, to prove the existence of a pivotal structure. Or maybe not at all, I don't know. Anyway. So, note that the equality T alpha, beta, gamma, delta equal T of alpha double star, beta double star, gamma double star, delta double star can be proved directly. In the pivotal case. In the pivotal case, remember that alpha double star can be replaced by alpha and adding some pivotal structure. So you had, so it's a good exercise, in fact. You can draw the picture, but you replace, you put that and you replace all that by what you get by the definition of pivotal structure. So you can replace alpha double star by some alpha and you add some pivotal structure. And all the pivotal structure will combine together. They will all vanish. And so you will get directly this will be directly equal to that. But what is very amazing here is we were able to prove that without using the pivotal structure. So this is interesting. The equality, not that the equality can be proved directly in the pivotal case, but so it is interesting that the previous theorem, the previous proof, it's interesting that we proved it without pivotal structure. But we proved it without pivotal structure. Not that existence of a pivotal structure in general is a famous open problem. So maybe, when I say maybe, I don't know, maybe not. Previous theorem can help to solve such a problem. But I did not think about that. So maybe not at all. I don't know. So it's just a remark like that without I did not check, I did not try. So okay, so can make the pause. Pause. Oh, a video. Okay, so next symmetry, and this symmetry will require, we will need the spherical structure following definition for 5.4. If C is spherical, then, and here we will use the lemma 2.13. Remember, this lemma involving the spherical structure, remember you have something like that, equal to something like that. So I said it's like if you move the this one string through in a sphere, something like that. So we will apply this lemma to prove the following symmetry of the monoidal tetrahedron. T of alpha, beta, gamma, delta equal T of so rho inverse applied 3 times to beta, rho inverse applied to sigma square of gamma, rho of alpha, rho of delta. And this corresponds to a cyclic permutation of these three. This one keep its place up to putting this natural transformation. And here this was moved here, this was moved here, and this here. So cyclic permutation. Okay. Okay. Alpha sigma. So the point is that I wrote, so where sigma is the natural transformation from definition 5.1. But in fact, rho is also defined as 5.1. Here, rho and sigma. So I should, in fact, add also. I don't know if I forgot to write that. Where rho is the natural transformation. Okay. So rho and sigma. Rho sigma are the natural transformation from this definition. So here I should add also where rho is the natural transformation from definition for okay. Poof. So as I said, we will apply the spherical structure. So by applying, so this was lemma 2.13 with x equal x6 and y equal x2 tensor x3 tensor x4. So we will. So I will this time I will draw the picture. I will draw the grouping. So as for the previous proposition, we will group together morphism. So we will have two blocks, and we will apply the lemma to these two blocks. But here it's a bit more tricky. So to be understandable, I have to draw the following two grouping of morphism. So let me quickly redraw the monoidal tetrahedron. So yeah, this one, this one go. This one go there, and this one go there. And finally, you have the big evaluation. Okay. So what is the grouping we are talking about? So here it's X, it's too small. X1, X2, X3, X4, X5. The grouping is the following. So we want X6. X6 is here, so we will cut something here. And we want 2, 3, 4. 2, 3, 4 are here. 2, 3, 4. So the grouping is the following. Like that. And like that. So here, 2, 3, 4. Okay. So here you have X6. And here you have, let me take another color. So this is X6 here. X6. And here it is X2 tensor X3 tensor X4. For these three strings. Okay, so you see, you have this block, you have one X6, and you have X2, X3, X4. Okay. So so you have this block and the other block. So maybe I should put it in red because it was written in red here. So one block, the other block, and you have the x6 and the x2, 3, 4, so x6, x2 tensor, x3 tensor, x4. Okay, and the lemma say that it is equal to, which is equal to by lemma 2.13 to something like that. So I will need a bit more space. And you have this monoidal structure here. No, not this one, not like that. So it's doing here something like that. And like, okay. So this is what the lemma is saying. So now you have to put this block here and this block here. And you will be able to prove the proposition. So we get so x is x. So we get the following. So let me see. Okay. Beta delta gamma delta k alpha. Not very easy to draw. Alpha. Ta, 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 ta. Okay. So, in fact, you will have a modification only here. All the other things will be the same. So, let me draw the modification first. So, A to X6 star. Yeah. Then that should move up as we have in the lemma. And I may draw the rest now. So now you okay. So sorry about this technical problem. We can come back. So we have a co-evaluation map also here. Okay. So evaluation map here. And here you have the usual as before. And B, this one, is connected to this one. And finally, you have that. And the big. Okay, so you have this big picture, which is exactly, as I said, putting this two grouping of morphism in this box. So you have this big thing, which is exactly this big thing, etc. So that's okay. But this is not, we are not finished here. This is not the shape of the monoidal tetrahedron defined initially. So we need more. We need more things. So we will apply some zigzag relation. So next, we need to apply some zigzag relation to realize the following move. Which can be drawn like that. You have a beta here, gamma, delta, alpha, and we want to move that here and to move that here. By doing that, we will get something. So we will move that here. You have it's open, and we will move that here. And then what you get, then everything will be okay up to applying some raw natural transformation, up to applying something like that or something like that. Okay. So after this move, we have alpha. So can I draw it in this small space? If I move that bit much as possible. Okay, I will try. So gamma, alpha, delta, beta. So here you have ax6 star square. Like that. Something like that. Something like that. Okay. So maybe I put the beta a little bit below. So that will go here. This is, yeah. So the drawing is not very easy. Anyway, up to zigzag relation, you understand the principle. This one will move to here. I don't have enough space. This is not easy. Ah là là. Let me move that a bit. I'm sorry, it's not very easy to draw. So I will try it. So this one is going like that. This one is going here. So this one going here. So it remains only here, this one, and finally this one. Okay. So I'm sorry about this one is not very clean. So this is, in fact, if you can do like that. Let me try. Okay. So everything reduced to some zigzagulation. So here you should be something like that to have a proper zigzagulation. But anyway, I hope you understood the point. So now we realize this move here. So we moved alpha here, beta here. So we move that here and that here by like that. So everything is okay up to some zigzagulation. Okay. And we need an extra move. And finally, and by lima 2.4 plus some zigzag again, you have okay, so what do we want? Okay, we want to realize this move. In fact, we are not happy with this one because in our model, the string are going on the left, and here they're going on the right. But we know we prove a lemma where, so a lemma like that. You have something like that with some beta. You have something like that, and this is equal to something else with beta double star like that. But here, our beta already like that, and we want like that. So we need to replace beta here by beta double left, double right dual. And it exists, the double right dual, the spherical case, I guess, yeah. Spherical imply rigid, imply existence of right dual. Okay, so what will with beta? So we have something like that. beta double right dual something which is equal to beta Okay, so we apply this lemma 2.4 like that. So what are the block here we need to consider? So this block and this block. So this block move here and here. We are doing like that. And here up to here. Okay. And you can put this one. So you have these two blocks. So these two blocks realize, and here you have some, if you want, you have some this one and this one realize this one. So we don't need the model to realize the full monoidal tetrahedron here. We just need to consider a piece, and this open here is just this one and this one. We don't need that because otherwise we'll have a problem with the closing string here. So we do that, and what we get is the following. So now we can move that, move the string the other way and put double star. This is exactly what we can do. So T alpha, beta, gamma, delta equal like that. So ga alpha, delta. Beta double right dual. Here you have the A to X star. Yes. Let me take as much as space as I need. That should be okay. 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 So now here. So this one, this move here. Okay, this one will move here. This one will move here. This one move here. So I'm sorry, the picture is not very beautiful, but in the paper it was written in LaTeX, so it would be much more easy to draw. I don't have time to do a better picture now. It's almost the end of the course with all this connection cutting. Okay. this one. And you have, I need more space. This. And here you need to do that. Okay. And I am almost done. We need just to draw the last. Okay. So I hope the picture is understandable, but it should be improved to be more clean. But I hope, so you should go to the paper. I draw it in LaTeX very cleanly. So what you have to observe here is now that we have the usual monoidal tetrahedron form up to the sigma and rho natural transformation. Here and here, here maybe 2 times, etc. So this is equal to T of, so here, double right dual of beta. Then here, you have rho inverse, and you apply 2 times sigma. Rho inverse, sigma square. Then you have rho of alpha and rho of delta. Rho of alpha, rho of delta. Okay. So here you really have rho, you have sigma square and rho inverse. Rho, etc. So you really have this. And finally, observe that the double right dual of beta is equal to rho minus 3 of beta. Because you have a beta rho inverse 3 times. 1 times, 2 times, 3 times. Let me do this. So let me go like that. This is equal to that, and this is equal to that. Okay. So we are done with this symmetry. So it was a bit hard to draw. Okay. So it's almost time. I don't have time to write something else. Let me just read the remark. So the next remark is saying that so the order in which the morphism appear in the right-hand side of the equalities for the last 2 propositions correspond to the cyclic permutation 2, 3, 4 and 3 to 1, which generates the alternative group A4. And the fact that it generates this group can be proved directly, easily by using gap. You take gap, you take the symmetric group of 4 objects, you take the 2 cyclic permutation, and you generate the subgroup by that, and you you see it is equal to F1. So I guess we'll stop here. And again, sorry for the 2 connection problem. So, okay. Off session. Okay.